Hi guys, hope you're all doing well today. Um, Today I'm going to present to you a model that I created about the current coronavirus pandemic. And it's sort of a take on a SIR model, which I'll sort of explain later. So um, I originally did this sort of PowerPoint slide presentation with my math class. And what it turned out to be was something pretty cool and something that um, it'll be interesting moving forward to kind of see what we end up with sort of this whole coronavirus pandemic. So today we'll sort of cover. I'll talk about, I'll just kind of talk about the introduction. We'll go over what the SIR model is and what my take was on it. We'll talk about how some of our data compares to the data of those like New York and some other places with coronavirus, and then we'll sort of talk about what this all means and then conclude. So to start about, this is a very sort of math heavy presentation, and I sort of plan to post this on YouTube or something like that, and so I'll try to sort of lower the math out of it a little bit more and focus more on what we got, and maybe that will help people maybe understand more of what we did. uh, so let's go ahead and get into it. So the sort of first thing we did is we took a look at New York, and we were interested in coronavirus, and we wanted to model something about that. We want to take our model and do something with coronavirus. So what did we do? So we looked at New York and we said, well, there's about 8.4 million people. What's something that we don't know quite yet about coronavirus? And so one of the first things that sort of came to mind was, well, we know people can get the disease. We know people become infected and then they either recover, or they die, or they become very sick. But then, can we become reinfected with coronavirus? And that was sort of a tough question because the answer is we don't know exactly, right? We think that we don't have a lifelong immunity, but we probably have some immunity after we become infected. So when we think about diseases like measles or chickenpox, once we get those viruses, our bodies typically build an immunity that is lifelong, and so we can never get those viruses again. Now, there's a few caveats with that. If you were on some immunosuppressants or some other different things, you may be able to get the disease again. But excluding those very few circumstances, you're always going to have immunity to that virus. So again, with coronavirus, we're not sure about what happens if you get it once. Can you get it again? Do you build lifelong immunity? And the question is, that was what we set out to model. We wanted to see what happens if there is a reinfection rate. And the hard part about this was sort of defining that reinfection rate. For a few reasons. One, we needed to define what an infection was versus a reinfection. So when you think of things like flu or influenza, you can get them 1 year, right? And then the second year you can also get it again. Does that mean you're becoming reinfected with the flu? And in our model, you aren't, right? So the new next year's flu is actually a different mutated strain. And so therefore you're becoming infected with a new version, and it's not a reinfection of the previous infection. So with coronavirus, we defined that a reinfection is the same infection of the same original coronavirus. Let's see here. So, what is an SIR model? Well, an SIR model is just a way to mathematically model what some of the basic things that happen during pandemics or epidemics. So how does it work? Well, let's just sort of define some of these variables, and again, I'll sort of take the shortcut on some of this math talk. But we have a couple of variables. We need to define a few things. We need to define the number of people who are susceptible to disease. We need to define the number of people who can become infected, and we need to define the people who have recovered from the disease. So these variables are just exactly what that means. And then we have a few, and then we have to define any of the number of people who become infected. You have to define the number of people who become susceptible, and you have to define the number of people who become recovered. And so it's probably much easier to kind of look at it like a tank problem, right? Because that's all we're sort of doing. So if we look at it like a bunch of tanks, we start with a tank full of water, and these tanks are empty as of right now. So we have tank S, tank I, and tank R, and this is like and there's certainly water in this tank, but imagine that it's completely empty, totally full. So at time 0, we sort of introduced this virus to the environment. And so what does that mean? Well, it means we have a little valve here. We need to open up this valve to let the water flow. So in tank S, we start with a full tank of water. And so tank S is the number of people who are susceptible. So if you look at a place like New York, there's about 8.4 million people who live there. All of them are potentially able to get the disease. So they all start in this tank. So then how many people are going to become infected with the disease? Well, it depends on how infectious the disease is, right? So how infectious is it? And you hear, numbers on the news and whatnot about it's, 1.9% of people are becoming infected and whatnot, or sort of different numbers kind of thrown around all the time. And that's sort of an evolving situation. But ideally, the idea is that, hey, at time A, we start the disease, and this disease has a 1.9% infection rate, or whatever you set it to. So the water start flowing at 1.9% into the tank I, right? So the number of people, this water tank is flowing down in the tank I, and these people are becoming infected, right? So this tank sort of pulls up. We have to say, well, at some point, people are going to recover from the disease. So when they recover from the disease, they're going to start recovering at a certain rate, and that's just rate B or beta. And we'll talk about those a little bit more further on. And so this sort of valve opens up, and people start coming up in the recovered. The water starts filling up in the tank R, which is people who've recovered. So hopefully that sort of makes sense. All this means is exactly what we sort of went through there. That's all that means. Our take on it was, hey, what happens if people are able to become reinfected? So what does that mean in this tank problem? Well, it means that we introduce a pump into the tank R, and we're saying, hey, some of these people who have become healthy and are fine again can now become reinfected and sort of thrown back into the susceptible population. And we have to define how fast this is pumping by this C, and later on we'll call this gamma. So how do we model that? Well, we just sort of threw some equations together that just say exactly what's going on in this tank at any given time, what's going on in this tank, and what's happening with this pump at any given time. And so that's what these added constants mean. Cool. So what did we kind of come up with? What did we do? Well, we made some graphs with our Python, which is sort of a programming language. We took a lot of our data from the NewYorkCity.gov website here, and we assumed that there was 3 cases. So there's when our alpha was greater than gamma, when our alpha was equal to gamma, and our alpha was less than gamma. So that could be confusing. So let me sort of clear that up a little bit. So in this first case, we have our gamma is less than our alpha. So what does that mean in context? Well, our gamma, if we go back to this tank equation, our gamma is a C, and so our gamma is the reinfection rate, and our alpha is how fast people become infected. So if our gamma is smaller than our alpha, what does that mean? It means that the rate at which people become infected, so the rate at which people become infected, is less than the rate at which people become reinfected. And we assumed that this was probably the most likely scenario. And why is that? Well, if you become infected, right, without taking sort of any social distancing or any sort of matters, you have a certain percent chance. And so in our case, we said you had a 1.9% chance of becoming infected with coronavirus. Now, what are the chances you become reinfected? So that means you became infected, you sort of got really sick for a while, and then you recovered. And now, what are the chances after you've recovered to become reinfected? Well, again, we've known that you probably have some immunity, probably not a lifelong immunity, so therefore you're going to be less likely to become infected. Secondly, if you became infected once and there was a chance you could become reinfected, well, you might do measures like wash your hands more, social distance, or do some of those things to become because you don't want to become sick again. So if that's the case, you're going to be less likely to become reinfected. And so we just sort of picked a number that was big enough to show a good graph, but small enough to be pretty accurate. And so we chose half of our initial infection rate. So we assumed this was our most likely scenario. And what does that sort of mean, right? What does that mean in context? So that means that if we start at time 1, so when the first initial person was infected, what happened with the number of people infected? Well, these are in days, so about 20 days, we didn't have that many infections. At 40 days, we didn't have that many infections. At 60 days, we started to see a really big spike in infections. And then at a certain time, about 80 days or so, we started sort of this decrease. And so this is what we modeled in New York. So again, I have 8.4 million people who are able to get the disease, and as they're getting the disease, they're falling into that infected population. and they're sort of leveling out and coming back up. And these are the number of people who have recovered. Now, again, this is our basic model, so there's a lot of things we're not showing in this, like deaths or measures taken to social distance, and all those things aren't really modeled. This is just saying, hey, we're not going to do anything about this disease. We're just going to let it run its course and see exactly what happens. So this is what we would see. So one thing about this, so this is the same exact graph. It's just sort of the time is sort of pulled out a little bit longer. And it was sort of interesting to see what happens. In math terms, we're sort of worried about the stability, or what are these graphs sort of after they do this sort of bob and weave, or they sort of level out at some point. What is that leveling out? What does that look like? And what we found was that if you took that this scenario, we found that they sort of level out at an infected of about 0.58 million people. So what does that mean? It means that in New York at any given time, over sort of this 400-day point, there's going to be about 0.58 million people who are infected with the disease. At 400 days or so, or further on, about 3.6, about 4.3 million people are going to be susceptible, or 3.62 are going to be susceptible, and our 4.3 million are going to have people have recovered. So what does that sort of mean? So how does that fit the data of New York? So I took this graph from the NewYork.gov website, and this was the number of people who tested positive over a given time. So how well does our graph, our model that we sort of just picked, we sort of just created with these parameters, how well does that fit this model? And I think it actually fits pretty well. So if we look around April or so, we have this really large peak in infections. Well, what do we see? We saw our peak in infections around times 60, so about 2 months in of the disease. If we look at this guy, we see that, well, this is from right from 3.8 to 4.5, so that's only about a month, right? So you're saying, well, why exactly does yours show 60 2 months versus their 1 month show its peak? And I think what happened is before this we didn't have a lot of testing, right? We weren't testing exactly for coronavirus, and so we don't know exactly what the rest of this data looks like, what the rest of this graph sort of looks like. And I think if we had that, we might see something that sort of looks more like our graph, more like this. And there's probably a lot of other reasons for it too, but I think this is actually, it does fit the data pretty well. We sort of see this peak sort of at a similar point in time. So I think it works pretty well. There's also sort of with this unknowns, a lot of people who are carrying the virus who are asymptomatic or had it and didn't have any symptoms, so there wasn't a lot of testing for that. And that's all part of the the reasons why our graph is a little bit different than what we see with the actual data. So here's our second scenario, right? So here's the idea that gamma is equal to alpha. What does that mean in context? Again, that means that if the number of people, if the chance that you are able to become infected, which is that 1.9%, is equal to the chance you become reinfected. So maybe you get infected once, you sort of get sick, recover, and then you say, you know what, I'm not going to take any more. I have no immunity built up. I don't care about taking any more measures to become reinfected, and so your chance of becoming reinfected is just as likely. Well, what do we see? We see a very similar sort of graph. It's sort of shifted to the right a little bit more, and our infections sort of peak around maybe a little bit around 80 days or so. And you can see all the numbers here, so it's kind of interesting. So again, we're more kind of concerned about the stability of these graphs. What do these end up with? Well, when gamma is equal to alpha, we see about 1.7 million people who stay infected with coronavirus at any given time. That's kind of interesting to see. So then we have our third case, right, when our gamma is greater than alpha. So again, what does that mean? Well, it means that the chance that you become infected with these originally is about 1.9% chance, but then the chance that you become reinfected is actually higher than the initial. So this is sort of a hypothetical case, right? Not super realistic, but it's sort of interesting to see mathematically. So if our reinfection rate is twice that of our actual original infection rate, what do we see? Well, we see a sort of this great similar shift, and the stability is what we're sort of caring about in these cases. And the stability is almost twice that. So that we have a number of infected people that are 1.76 million people in New York are always going to be infected. So if you compare all three of these cases, we can sort of see that in case one, our most realistic case, we're initially going to have 0.58 million people infected with coronavirus at any given time in New York. Case 2, that almost doubles, right? We have a doubling of when our reinfection rate is equal to that, and this is, possibly realistic. Case 3 is our, unrealistic, our hypothetical scenario, and we have again almost another double of our infections stability. So how do we sort of use our initial conditions to build these models? Well, we started with 8.4 million people. We just sort of looked back at data, and this is a pretty hard thing to figure out. So what is this saying? This is saying at time 0, how many people were initially infected. Hard thing to figure out, right? Initially, probably one person brought it over from Wuhan or whatever, to the United States and landed in New York. And so there's probably one person at some time, but for our scenario, we sort of just chose 18 or 28, sorry. And if there's nobody there's only 20 people who are infected, then there's nobody who's recovered. So how do we build our equation with our modeling reinfection disease? Well, again, all we talk about is we have these tanks, and we're just saying, hey, at any given time, what's going on with this tank? That's all we're saying. So the initial SAR model without this sort of pump is just saying, hey, at any given time, what's going on? Well, we know at any given time we have some water coming out, right? We have some water coming out, and it's going out at a rate of how big this valve is. So that's sort of a minus ASI. So that's exactly what that models, right? At any given time, we sort of have water coming into this tank and water pouring out of this tank. So that's how you model this infection tank. And for our recovered tank, we're just adding water in the basic SIR model. So you're just saying, hey, I gain water at this certain rate. For our model, all we needed to do was add a little bit of where water was coming in, or infection rates in our case, right? So we're getting pumped water into this tank, so we have to add a little bit here, and on the recovered tank, we're taking a little bit out, so we're sort of taking a little bit out there. So again, how do we do this? Well, we had our 3 infections coefficients. We had our alpha, beta, and gamma. We also saw that as C. We used our Python code, and we created this code to sort of create and model these functions. If you guys are interested, I'm happy to share this code with you. It was pretty cool how we came up with it. And you could, and if you're interested or wanted to, I could give this to you, and you could play around with some of these coefficients and just sort of see what happens. That's sort of kind of a cool thing. So what did we sort of learn from this, and what did we find? Well, we found that when you have a reinfection rate, it means that you're going to always have some sort of infection always in society, right? So rather than an overall pandemic, we're going to have an endemic now. We found that it was pretty hard to sort of model some of these things with our available data, because we could only compare our data with what we already had, right? So going further, we haven't had enough time with coronavirus to see how accurate our graphs are. So what do we sort of learn from this, right? So we learned that if we have an infection rate, so again, we're not entirely sure if we have we know we have an infection rate, but if we have a reinfection rate, what does that mean? We learned that if you have a sort of a reinfection rate, depending on that infection rate, what the number is, leads us to an endemic, not necessarily a pandemic. So an endemic is we're going to always sort of live with coronavirus in society. Our model actually predicted that we're going to have about 0.58 million people that are constantly going to have an infection of coronavirus, asymptomatic or not, in New York. We also learned that as we sort of increase that reinfection rate, then that infection stability is also going to increase. So we did this model, and we thought it was pretty cool, and so I decided to post it with you guys, or share it with you. Yeah. Anyways, yeah. So we still have some references for how we got our data and how we modeled our equations. So I thought that was pretty interesting. If you guys have any questions, feel free to ask, or yeah. Anyway, hope you all have a good day. Adios.